Wood combustion is far more complex than simply lighting a match to a log. When wood burns, it undergoes a sophisticated series of chemical and physical reactions that transform solid wood into heat, light, gases, and ash. At its most basic level, wood combustion combines wood with oxygen from the air to produce carbon dioxide, water vapor, and energy in the form of heat and light. However, this simple equation masks a much more intricate process. Wood combustion can be broken down into four distinct stages. First, drying removes moisture from the wood. Then pyrolysis breaks down the wood structure. This is followed by flaming combustion of gases, and finally, glowing combustion of the remaining char. Understanding these combustion stages is crucial because different burning methods produce vastly different levels of harmful emissions. As this comparison shows, traditional fireplaces produce the highest emissions, while modern certified stoves and gas furnaces produce significantly less pollution. Modern stove technology has revolutionized wood burning. Eco-designed stoves can reduce harmful emissions by up to 95% compared to older models. These improvements come from applying our scientific understanding of combustion chemistry to create more efficient and cleaner burning systems. In the following sections, we will dive deep into each stage of wood combustion. We'll explore the chemistry behind moisture removal, how wood breaks down into combustible gases, the science of flame formation, and what creates both useful heat and harmful emissions. This knowledge is essential for anyone interested in efficient, clean wood burning. The first stage of wood combustion begins with drying, also known as dehydration. This crucial process prepares the wood for the chemical reactions that follow. Fresh wood contains significant amounts of moisture trapped within its cellular structure. These water molecules must be removed before the wood can undergo thermal decomposition. When wood is heated to temperatures between 30 and 150 degrees Celsius, the drying process begins. We can monitor this temperature increase using a thermometer. As heat is applied to the wood, the temperature gradually rises. The mercury column in our thermometer shows this temperature increase from 30 degrees Celsius upward. During this heating process, the water molecules within the wood gain energy and begin to change from liquid state to gas state. This is the fundamental chemical transformation of the drying stage. As the temperature reaches the optimal range, water molecules evaporate and escape from the wood as water vapor. This removes the moisture content that would otherwise interfere with combustion. This drying process is essential because it prepares the wood for the next stage of thermal decomposition. Without proper moisture removal, the subsequent chemical reactions cannot proceed efficiently. The drying stage transforms liquid water into water vapor through controlled heating, creating the foundation for all subsequent combustion processes. Following the drying phase, wood undergoes pyrolysis, a crucial thermal decomposition process that transforms solid wood into volatile gases and char. Pyrolysis occurs at temperatures between 200 and 500 degrees Celsius. This is significantly hotter than the drying phase, requiring substantial heat input to break down the wood's molecular structure. Pyrolysis is an endothermic process, meaning it requires continuous heat input. Crucially, it occurs in the absence of oxygen, distinguishing it from combustion. To understand pyrolysis, we must first examine wood's composition. Wood consists of three main components that each decompose at different rates and temperatures. Wood is primarily composed of cellulose, making up 40 to 50%, hemicellulose at 25 to 35%, and lignin at 20 to 30%. Each component has a different molecular structure and decomposes at different temperatures during pyrolysis. Now let's examine the specific chemical breakdown using cellulose as our primary example, since it's the most abundant component in wood. During pyrolysis, cellulose molecules break down under heat to produce numerous volatile gases and a solid carbon-rich residue called char. The volatile gases produced include carbon monoxide, carbon dioxide, methane, hydrogen, acetic acid, tar compounds, methanol, and formaldehyde. These gases will later participate in the combustion process. The remaining solid material is char, a carbon-rich residue that forms the glowing embers we see in wood fires. This char will burn much more slowly than the volatile gases. This thermal decomposition is endothermic, meaning the wood must continuously absorb heat energy to break the molecular bonds. The absence of oxygen prevents combustion, allowing the wood to decompose rather than burn. Pyrolysis is a critical stage that prepares wood for combustion by creating the volatile gases that will fuel the flames in the next phase of wood burning. When pyrolysis gases are released from heated wood, they begin to mix with oxygen in the surrounding air. This mixing sets the stage for the dramatic flaming combustion phase. The fire triangle shows us the three essential components needed for combustion: fuel in the form of volatile gases, oxygen from the air, and sufficient heat to trigger ignition. One of the most important combustion reactions involves methane gas. When methane combines with oxygen, it produces carbon dioxide and water vapor in a highly exothermic reaction. The methane molecule has a tetrahedral structure with carbon at the center bonded to 4 hydrogen atoms. This stable structure releases significant energy when it reacts with oxygen. Another crucial reaction involves carbon monoxide, a toxic gas produced during incomplete combustion. When carbon monoxide encounters oxygen, it forms carbon dioxide in a reaction that helps complete the combustion process. These combustion reactions are highly exothermic, meaning they release enormous amounts of energy in the form of heat and light. This energy release creates the visible flames and intense heat that characterize the flaming combustion phase. The flaming combustion phase represents the most visible and energetic part of wood burning. The rapid oxidation of volatile gases produces the dancing flames we see, while releasing the thermal energy that makes wood such an effective fuel source. During the flaming combustion stage, not all fuel burns completely. When there is insufficient oxygen or poor mixing, incomplete combustion occurs, leading to the formation of soot and smoke. In complete combustion with sufficient oxygen, wood burns cleanly, producing mainly carbon dioxide and water vapor with minimal harmful byproducts. However, when combustion is incomplete due to insufficient oxygen or poor air mixing, the flame becomes smoky and produces harmful byproducts, including soot and various toxic gases. Soot forms when carbon-rich fuel molecules break apart in the high-temperature flame, but don't have enough oxygen to completely oxidize into carbon dioxide. Instead, these carbon atoms cluster together to form tiny black particles. Smoke contains various harmful gases produced during incomplete combustion. Carbon monoxide forms when there isn't enough oxygen to fully oxidize carbon to carbon dioxide. Unburned hydrocarbons escape as volatile organic compounds. Smoke also contains irritating compounds like aldehydes, including formaldehyde and acetaldehyde. These chemicals cause the stinging sensation in your eyes and throat when exposed to wood smoke and can be harmful to respiratory health. The presence of soot and smoke are clear indicators of inefficient burning. Visible smoke, sooty flames, and the release of harmful compounds not only waste fuel energy, but also contribute significantly to air pollution and pose serious health risks to both indoor and outdoor air quality. Understanding soot and smoke formation is crucial for optimizing wood combustion systems. Proper air supply, temperature control, and fuel preparation can significantly reduce these harmful byproducts, leading to cleaner, more efficient burning. When wood burns completely, it produces 3 main categories of combustion products: gases, solids, and particulates. Each category contains different chemical compounds that result from the complex combustion process. The gaseous products are the most abundant combustion products. The primary gases include carbon dioxide and water vapor from complete combustion, along with carbon monoxide from incomplete combustion. Carbon dioxide is the primary product of complete combustion. Each molecule consists of 1 carbon atom bonded to 2 oxygen atoms through double bonds. Additional gases include methane from pyrolysis, nitrogen oxides from high-temperature reactions, and sulfur dioxide when sulfur is present in the wood. The solid products of wood combustion consist primarily of ash. Ash contains the mineral residues that were originally part of the living tree but cannot be burned. These minerals include calcium from cell walls, potassium from plant nutrients, magnesium from chlorophyll molecules, and silicon absorbed from soil during the tree's growth. Particulate products are fine particles suspended in the combustion gases. The 2 main types are soot and tars, both resulting from incomplete combustion processes. Soot consists of unburned carbon particles that appear as black specks. These form when there is insufficient oxygen for complete combustion of carbon containing compounds. Tars are complex organic compounds that condense from the volatile gases produced during pyrolysis. They appear as sticky, dark substances and can contribute to air pollution. Wood combustion produces a complex mixture of gases, solids, and particulates. Understanding these products is essential for optimizing combustion efficiency and minimizing environmental impact. Wood combustion involves 4 distinct chemical stages, each occurring at specific temperature ranges and producing different products. First, drying removes moisture from wood between 30 and 150 degrees Celsius. Then pyrolysis breaks down wood structure between 200 and 500 degrees, creating volatile gases and char. Flaming combustion burns the volatile gases with oxygen, producing visible flames and heat. Finally, char combustion slowly oxidizes the remaining carbon at 400 to 800 degrees Celsius. Modern wood-burning technology has revolutionized efficiency and environmental impact through innovative engineering solutions. Modern wood stoves achieve 80% efficiency compared to just 15% for older models, while reducing harmful particulate emissions by up to 95%. Advanced pelletization processes convert wood waste into high-energy density fuel pellets through sophisticated manufacturing systems. Emerging technologies like combined heat and power systems and wood gasification are pushing the boundaries of wood fuel utilization. These innovations align with increasing demand for renewable energy and stricter environmental regulations, making wood combustion a key technology for sustainable heating and power generation.